Hi guys, Black Box here. Another video, and this time it's about the A320X operating speed definitions. I know it sounds kind of boring, but trust me, there are some speeds that you'll need to know about, especially when it comes to the symbols on the primary flight display or the different abbreviations in the MCDU. So let's get started straight away and have a look at the different operating speeds which you'll find in the A320. You'll find the operating speeds divided into 4 categories, and these are the so-called characteristic speeds, protection speeds, limit speeds, and then you have other speeds. So here are some examples of the different speeds. For example, you have the characteristic speeds like F speed, S speed, green dot, or in the protection speed section, the V alpha prot, the V alpha max, etc. etc. The limit speeds, well, obviously you have flap extended speed, the max landing gear extension speed, the maximum operating speeds, etc. And other speeds are defined as V1, VR, V2, VREF, and V approach. So let's look at those speeds in more detail, and we'll start off with the so-called characteristic speeds. Now, to some basic theory, the characteristic speeds in the A320 are computed by the flight augmentation computer according to the gathered aerodynamic data. Now, the lowest speed you can have obviously is the so-called stalling speed, VS. However, the VS is not displayed anywhere in the A320. Now, since most of you know that the A320 with its flight control computers has a stall protection system, the A320 cannot be stalled in the normal law. And so you cannot take the typical stalling speed from a conventional aircraft, i.e. the speed where the lift suddenly collapses. In the A320, you have to reference that differently, i.e. you have to reference that to a speed value that you can actually demonstrate during flight tests. And so the airworthiness authorities have accepted a new definition of the stall speed in the Airbus, and that is the stalling speed at 1G load factor, i.e. the VS1G. And that is the lowest speed at which the airplane can develop a lift force which is equal to its weight and to keep a 1G flight path. Or if you want to define that differently, it corresponds to the maximum lift coefficient just before the lift starts decreasing, and with the load factor still being 1G. And so you come to a formula where you reference that to the VS min, i.e. the stalling speed from conventional aircraft. And so VS1G times 0.94 is equal to VS min, i.e. the stalling speed from conventional aircraft. Let me show you a chart where you have the lift coefficient on the y-axis and the angle of attack on the x-axis. And you can see that with increasing angle of attack, obviously the lift coefficient increases, and you reach a maximum lift coefficient at the 1G stall speed. Now in the chart you can also see the old stall speed, and the difference between the new and the old stall speed is the factor 0.94. So why is this important? Well, in conventional aircraft, we know that the VREF for approach, for example, gives us a buffer of 1.3 times the stalling speed, i.e. if the stalling speed were to be 100 knots, then VREF would be 130 knots. And that means for the A320, we have to multiply that by the 0.94 factor that we've just talked about. And hence, the A320 VREF equals 1.23 VS1G. And guys, please don't get too worked up about this. I'm just stating some definitions here. Flying-wise, all you need to know is that if you look at a reference speed for the approach, you know that you have a 1.23 or 23% buffer to the stalling speed of the aircraft. All right, let's come to the VLS speed, the lowest selectable speed, and that is the top of an amber strip on the primary flight display speed scale. Now the VLS on the FSLabs A320X is computed by the FAC, Flight Augmentation Computers, and they are based on the aerodynamic data, and that corresponds to 1.13 VSTOL during takeoff, and after takeoff it becomes 1.23 after you retract the flaps by one step, or 1.28 when in a clean configuration. And be aware that VS1G obviously always takes into account the current configuration of the aircraft. Now during the takeoff roll, you'll notice that VLS is not displayed, and that is because the flight augmentation computers only calculate that after the liftoff. And after liftoff, you can see the V-alpha prot band appearing, and because of the high G load at the beginning of the rotation, the VLS comes visible a little bit later. But here it is, and the VLS in this case is 135 knots. Now, needless to say that if you, for example, extend the speed brakes, then obviously the VLS changes as well. And that is because the speed brakes increase the stalling speed of the aircraft. Now, likewise, increasing the flap setting lowers the stalling speed, and hence VLS is always decreasing as well. And the other way around, if we're decreasing the flap setting, then obviously the stalling speed increases and VLS is also adjusted accordingly. Another characteristic speed is the so-called F speed, and the F speed is the minimum speed at which the flaps may be retracted at takeoff, or during the approach. F speed is used as a target speed when the aircraft is in config 2 or 3. So during a takeoff with config 2 or 3, or during a go-around, whenever the actual speed is above F speed, you are allowed to select flaps 1. And why not 0? Well, because for the config to go to 0, it would mean that you are retracting the slats as well. And for slat retraction, you have another characteristic speed indication called the S speed. The S speed is the minimum speed at which the slats may be retracted at takeoff, or during the approach. The S speed is used as a target speed when the aircraft is in config 1. Okay, so then we come to the last characteristic speed we would want to talk about today, and that is the green dot speed, indicated by a little green circle on the speed scale, and that indicates the engine out operating speed, or otherwise known as the best lift to drag ratio speed. And so in case of an engine failure, you would try to fly the green dot speed. The same principle applies for holding patterns. Obviously, the green dot speed will mean that the fuel burn is the least, and hence when flying holding patterns, always aim for the green dot speed. Now we come to the next section, and that is protection speeds. And here in particular we have V alpha prot, V alpha max, stall warning speed, and the Vmax. So the maximum airspeed allowed with the current configuration of the aircraft. So when looking at the picture here, you can see a chart on the right hand side and the indications on the primary flight display. We've talked about VLS, and then if you increase the angle of attack further, you will get to the V alpha prot area. That's the orange and black ambered strip. And if the speed drops into that area, then at some point the angle of attack protection becomes active. You will notice that with alpha floor being displayed in the primary flight display, mode annunciation, and also on the engine warning display between the N1 indications, it will also say alpha floor. And in this case, even when auto thrust is off, auto thrust will engage and toga power is applied automatically. And then there's the V alpha max, and that is the maximum angle of attack speed, and that's the speed represented by the top of a red strip on the primary flight display speed scale. And in normal law, that is the minimum speed that no matter how far you pull the stick back, that's the lowest airspeed the fly-by-wire system will allow, and hence you cannot stall the aircraft. Now that is different in alternate law. Here it is actually possible to stall the aircraft, and hence that is why you have a stall warning speed, and that is defined by a red and black strip on the primary flight display speed scale. So we come to the last of the protection speeds, and that is Vmax, represented by the bottom of a black and red strip on the speed scale. It's determined by the flight augmentation computer, and it's always corresponding to the present aircraft configuration. It shows the maximum speed for clean configuration, for landing gear extended, or flaps extended speed. Now these speeds go hand in hand with the next category of speeds called the limit speeds, and here as well VFE, VLE, VLO, VMO, and VFE next are all limit speeds that are symbolized on the primary flight display speed scale. And by the way, the VFE next symbol are the two amber strips, and those represent the maximum speed for the next further extended flap lever position. Now please note that the maximum speed for the flap position is linked to the flap lever, and so once you move the flap lever to the next higher position, the limit speed will immediately decrease and be shown on the primary flight display, even though the flaps have not reached that flap position. And we come to the last category, the so-called other speeds. And I'm sure that all of you have come across at least some of those speeds. So we'll start with the first one called V1. And V1 is the highest speed during takeoff at which the flight crew has a choice between continuing the takeoff or stopping the aircraft. And on the primary flight display speed scale, the V1 speed is indicated by the number 1. Next up is the VR, the speed at which the pilot rotates the aircraft in order to reach V2 at an altitude of 35 feet at the latest after an engine failure. And on the primary flight display, VR is indicated by a small cyan circle. And then there's V2, and V2 is the takeoff safety speed that the aircraft attains at latest at an altitude of 35 feet with one engine failed, and maintains it during the second segment of the takeoff. And the V2 is indicated by the speed select symbol on the speed scale. Let us now look at the approach speeds. Now, on the approach page, it says VLS. It does not say VREF anywhere. However, be aware that VREF is the reference speed used for normal final approach, and that equals 1.23 times VS1G, and is valid for config full. And so the VLS config full is in actual fact the VREF, and that is equal to 1.23 times VS1G. So for config 3, you'll get a different VLS speed, but that is not defined as VREF. Right, the last speed we'll be looking at now is the V-approach speed, and that is the final approach speed, and it's calculated by the FMGCs. Now it's represented by the following formula. So the V-approach equals VLS, either config full or config 3, plus the wind correction. It's limited by a minimum of plus 5 knots and a maximum of plus 15 knots. And hence, when you insert the wind with a headwind component of less than equal to 15 knots, it doesn't really change, or it doesn't actually change the V-approach speed. Only if you get more than 15 knots headwind component will the V-approach get above plus 5 knots. So let me just demonstrate you this. So at the moment we have crosswind of 14 knots. I will change that to a headwind of 15 knots, and you can see that the V-approach is plus 5 from VLS. If I increase that to, let's say, 18 knots, then VLS plus 6 will make up the V-approach speed. Headwind component 24 knots, you guessed it, plus 8 knots from VLS. And so on. So now we have 11 knots addition to VLS. And if I insert 45 knots headwind component, or almost 45 knots, then we reach the maximum of 15 knots addition. And from that point onwards, it doesn't matter how many knots of headwind I add, it will stay at plus 15 knots. If that changes to complete crosswind, so we have 60 knots crosswind, well, guess what? Then the approach is VLS plus 5, because that's not a headwind component. I hope that has clarified the approach function in the MCDU. And that, ladies and gentlemen, completes the video on operating speed definition. I hope it wasn't too boring. I know it's a very dry kind of topic, but maybe I managed to clarify a few things for you. I will end this video here with a nice approach into Samos, runway 09. You guys know that I love this approach. And so until the next video, as always, take care. Thank you very much for watching, and happy landings.
500. 400. 300. 200. 100. 50, 40, 30, 20, retard 10.